All right, ladies and gentlemen, Happy New Year to everyone. Welcome to the virtual January 2022 monthly meeting of the Minnesota Astronomical Society. I guess I'm not your host, Matt's the host, but I'll be your host tonight um, without the controls. And so welcome everybody, and thanks for understanding for us just kind of pulling a quick change there as of over the weekend to do this virtually rather than hybrid. Um, it was a hard decision, but then once we pay attention to the news a little bit, and it was an easy thing to do then. So thank you for that. Thank you for being with us tonight. And let's kick this thing off. Oh, let's see, we have a problem. There we go. Here is the new board. Incoming Vice President John Zimmich, and then you reelected Matt Dunham, the treasurer, and Conrad Sanders, board member at large. And John, maybe just take a few seconds, introduce yourself. There's our faces.
Hello. I guess you saw my face up there. You can see it, so I don't need to turn my video on. But I guess be jumping in here. I've already done quite a bit working with vaults and with Mark and Anton with the Lunar Scope program, and jumping in, doing a number of things, financial, and just getting administrative things down. But that was a hard-fought election, and I guess now I'm just gonna focus on getting everyone together after that.
All right, cool. Thank you, John.
Okay.
And the rest of the board: Matt Dunham, the treasurer; Trina Johnson, our secretary; and Gunnar and Conrad, our board members at large. It's a great fun when we all get together, especially this month. Now it's budget time, so those site leaders out there that owe us budgets, I think there's only one. Please get those in as soon as you can, so we can start putting that together. I also want to welcome all new members. There's quite a list, and here they all are. Welcome. As I say every month, this club is, you can get as much out of it as you put into it. And if you want to be involved, there's certainly many, many opportunities. And I certainly want to be the person to encourage you to get involved with the sites. There's always opportunities to get involved in the leadership of this organization also. So, I'm here to encourage you and guide you and lead you. If you have any questions, I can answer those, as well as any of the board members. And you just go on our website and go on to contact us, and you'll find a way to get a hold of somebody if you want to get involved. We certainly can help you with that. So welcome new members. We appreciate you. The rest of the membership, I mean, it is what it is, because we are all volunteers to this organization, and that's what keeps the machine running, as I like to say. So thank you, volunteers. Especially all you site leaders and committee members. You guys work hard. You guys work hard all year. But I know you recently have worked hard, because I know you were preparing budget numbers for us to consider and gather and get together and present for next month's meeting. And then our volunteers for the December BSIG meeting. That's very important. And I know there's work being done on the MAS website yet, and that's moving along, and we'll get it. We'll get it before spring, I'm pretty sure. And then I want to take just a special time to thank Walt Streibergs for his work on the board. He was very supportive of me the last year that I've been president, and I know he's been on the board, I swear, for a long time. I was trying to think of how long it's been since he wasn't on the board. And so that I know it's been a while. So I want to especially just call him out and say thank you. He's going to be around. He's not going anywhere. He's just not going to be on the board. And I know he is instrumental in the management of the background of all the Google stuff, the email addresses and the drives, and he's working on the website, and he's been organizing that. So thank you, Baltz. And if you have anything to say, this is your spot right here. The light is on you.
All right. Well, thanks, Mark. Just want to thank everybody as well for all the support over the years. And like Mark said, I'm not going away. I'm committed to following through with the new website. That's still ongoing, and we, like Mark said, we want to get that done before the observing season starts. So to get that working, and I'll still be around on the various committees that I'm on. So I'm not going away.
Oh, good, because I don't know what we'd do without you. So, all right, thank you, thank you. Thank you, volunteers. And I only put these up as just as a few things that I think of when I'm preparing this slide. I know there are others. I could call another person out. Lila. Lila does outreach stuff. I see outreach stuff going on all the time when I'm following the forums and things like that. So, I mean, that's another person that doesn't really get mentioned here very often, but she does big things. She keeps that thing organized, and it's a very well-run, fine-tuned machine. She does a great job, and connecting club members that want to do outreach to people that are interested in outreach. So she does a great job there. So, all right, we're going to try this again. We're going to try next month to have a hybrid meeting. Stand by, because if it stays at the levels that we are today, then we're going to be back here and we're going to be looking at each other through Zoom again. And we'll just watch, and we'll try to give you a few days notice, and we'll hit you up with an email blast and Slack and the forum and however else we can try to get that updated, the website and things like that. So at this time, I'm going to say we'll see you next month at the hybrid meeting, but I want to be cautious. There are just too many people that this club would care about. If something happened, I wouldn't feel very good. Let me just say that. So hopefully we see you next month. We had yesterday we had another test run over there. We really got it fine-tuned now. I think we have everything we want. We should be able to put on a pretty good presentation on both sides. I don't think anybody's going to feel left out, whether you're on the Zoom call or whether you're in person. And then also, if you miss the meeting, it's going to be recorded, and I'll take it in there and edit it and get it out as quick as I can after the meeting. So stay tuned. Thank you for your patience. And we're still kind of looking. I don't know. Matt stepped in. Matt's going to do this, but I don't know. It sure would be nice to have maybe another person to be there to just assist and help us run the meeting when we're on site, when we're face to face. It just would make it easier, because I probably could do it, but I don't want to try and do a slideshow and mess around with the controls to turn mics on, turn mics off, things like that. So, it's not that hard. Of course, maybe I'm speaking for Matt. So Matt, you can chime in. If to me, it didn't look like it was that hard. In 15 minutes yesterday, we had it running. So, I think it's going to work. So.
Yeah, it's not too complicated, but I think it'll be really handy. I was impressed how well it did work.
Yes, so it's way better than it's way better than it was the last time we were there. We kind of struggled, but it's better. It's great, and the room is great. Just let everybody know, plenty of space, but we don't want all 670 of you showing up. So that would be a little crowded, and I don't know, might be dangerous. All right, just a reminder that we do have that Slack tool, and there's just if you're interested in signing up, Slack at mnastro.org, and somebody will take care of you and get you signed up and get you in that group. Those channels work very well. I recently have been using the video chat. The video has worked very well. With a couple people, I've done that. It works really well. You can share screens, and you can have as many people on that as you want. And it's free. That's what's really cool about it. And there's no limits like you would have like on Zoom. If you don't have a paid account, or if you have Google Meet. If you're using Google Meet, you have time limits there too. You can't go over an hour. I had a 90-minute conference here the other night, so it works well. Check it out. Don't forget that MAS is on YouTube, and the best way, you can get that link there, but that's kind of a pain. But if you just go to any browser and just do Minnesota Astronomical Society YouTube, it pops up pretty close to the top 1, 2, something like that, and it'll get you there. We post this monthly meeting will be posted there, maybe by Monday, and the special interest groups. The last BSIG is up there. That was there. I saw it, and I'm a imager, an astrophotographer. We time to time we have a special meeting. We post those too. We record those and post those up there too. So a little bit for everyone, and then you can go backwards in time and check us out, see what we've done before.
Yeah, and I like to say, if you're not a subscriber and you go to that page, the channel page, then the introductory video is called "Join Us for a Star Party," I believe, and it's a really good overview of the club. It was put together a few years ago, and it really does a great job of explaining all about the club.
Yes, I agree. And there's also Steve Emirates, welcome to the club thing too. That's up there. There's a lot of good things. So check it out. It's good stuff. Anton Gregory, are you on the line tonight?
I see Anton.
Okay.
There we go. Hi, Anton.
Right. Yeah, I was trying the spacebar method. Apparently that doesn't work very well. So anyway, yes, we have our Lonerscope program, and we are in business year round. It's still a popular program. In each of the last 2 years, we've loaned telescopes out 87 times. So and it's very popular with a lot of our new members. In fact, I recognized a couple of those names you posted earlier. Anyway, cool. Our members, of course, can request, here we go, telescopes and these DVDs on our website under members, Lonerscope program. Just request whatever telescope or DVD you would like. And the arrangement is you visit me at my home, and we check them out. We have 16 telescopes now. Some Smith-Cassegrains, Dobbs, refractors, and a solar scope. So there should be something there for everybody. Again, if you're interested in borrowing a telescope, just go online and make the request through the website.
Awesome. Thank you, Anton. I still want to check out one of these DVDs, but just can't find time. So that's awesome. That's really great. Thank you, Anton. Anton does a fabulous job. So some events before the next meeting. I kind of struggled this month putting this list together because I went, it's kind of boring. Venus is at inferior conjunction, and then Mercury's going to be at inferior conjunction. And I just kind of give it the, okay, it is what it is.
And what does that mean?
What does that mean? What do you mean?
Oh, the inferior conjunction.
Oh, inferior conjunction. Oh, everybody knows what that is, Matt.
Okay.
It's when the Venus or Mercury is in between us and the sun. How's that? You can't look at it because it is by the sun. And I guess, I guess I haven't looked to see what the angle difference is between actually Venus. Does it pass above or below? Which obviously it does. And how far away is it? Because I've actually imaged Venus within a day or so of the inferior conjunction. And it's tricky. You have to be careful because you don't have a solar filter on your scope, and you could potentially get some things hot. But I have images of Venus within, I think, 24 hours of its conjunction, and it's pretty cool. I'd never try Mercury. It's just too small. I'm not that, and I think its orbit is way too flat. I wouldn't want to try it. But Venus, when it's far enough away, I certainly would do it. And I did it with a 14-inch Schmidt Cassegrain, so I did have all kinds of shielding up to keep the sun out of the scope. So that was fun. So I mean, there's Mars is close. I forgot to take that occultation not here out. That's not true. So apologies. We have an error on my slide. And then the February 6th hybrid meeting is on there also, and the new moon. I always get excited about new moon. So upcoming star parties. There are none on the schedule, but I just want to remind everybody that CGO is always open. And ELO and ELL is also open too. You just have to post on the forum to let us know you're going there as members. There's no public events. And I also wanted to use this slide if there's any of the site leaders that would have something to say, this is a place for you to chime in. All right, very good. We're going to move on.
Well.
Oh, wait a minute. Okay.
I was waiting for Trina to chime in, but I'll chime in instead. Since I don't know how many people know, but since our last meeting, we had some damage at Cherry Grove Observatory from the storms on the December the 15th. And it turns out, if you look at the track of the tornadoes that were down there, we were about a half a mile southeast of a track of an EF2 tornado. We did sustain some damage down there to the fencing. I think there was 5 sections of fence that were blown down. Poles were snapped. I mean, it was pretty, those are 4x4s that are fairly new. So it was a pretty substantial wind. We lost a piece of the roof of the shed, the utility shed down there. And the roof of the observatory was moved enough that the wheels at the southern end were up off the track. And if you know anything about Cherry Grove, that's a very heavy roof. So it must have been some really substantial winds to move the roof that much. We were able to put the roof back in place, and it works fine. There was no equipment that was damaged, so we're fortunate there. We did have the inspector down there this past week. Steve Emmert met with him down there on Tuesday, I believe. And so we'll be seeing what we get in terms of insurance monies on that. And there'll be some work parties in the spring to repair that stuff. But fortunately, although there was some damage, nothing that was terribly serious.
Very good. Thanks for that update, Dave. Any updates from LLCC or ELO or even JJ Casby?
So about the wind, then, did you end up with damage that prevents the roof from being moved now, or is it back on the track?
It's back on the track now. It could not be moved before. We tried moving it, and it was wedged. But once we got the wheels back on the track, then it worked fine.
Thank you.
Cool. All right. Next up. COVID. Yep. So if you're indoors at any of our facilities with other people, please mask. That's all we ask. Impromptu star parties. There's no restraints other than if you are inside. But if you're outside, obviously, there's no restrictions. And hey, go have a good time. BSIG. Sherry Jones, are you on? I know I spoke to you specifically about this.
Good afternoon. Good evening, everyone.
Hi, Jerry.
So what would you like to know about the BSIG?
Well, what are you going to talk about, Jerry? Give us like 5 minutes.
So the official title is
Not
looking
organizing your evenings.
The official title is Organizing Your Observing Evenings with and Without the AL Observing Programs. Now, I'm guessing most of you know that one of the hats that I wear here at MAS is that I'm the Astronomical League coordinator. And so I'm the person who is supposed to know stuff about the observing projects that the Astronomical League puts together for us. And I thoroughly enjoy that job. I thoroughly enjoy reading the logs that are sent to me for all the certifications and the pins. And so when Suresh approached me to do this, originally the idea was, well, why don't you just give us a bit about the AL programs and just the observing programs, what they are, yada yada yada. And I'm more than happy to do that. But as I thought about that, I wanted to expand that a little bit more, because some people are interested in doing the observing program, some people aren't. But really what the observing programs are, at least in my opinion, it is an opportunity to organize our observing evenings. And as I thought about that a little bit more, I decided I wanted to branch out a little bit and really talk more specifically about how do you organize an observing session? What are some of the things that go into it, or should go into it to have an effective observing session? And I came up with what I called limitations. I think I have 9 limitations, and they're not really limitations, but they're things that really you ought to know that affect what you will do, what you can do, what you can experience, what you should prepare for, yada, yada, yada. And some of them are as simple as just what kind of telescope are you using? Because there are certain things you can see better with one type, and certain things you can see better with another type. And so it's kind of an amalgam of a lot of the lessons that I've learned over the past decade or so of being a real serious observer. And so I'm going to kind of nest that together. I'm going to start with giving a presentation of just what are some of the things like air mass, sightlines. How does air mass affect sightlines, or how does sightlines affect air mass? Makes a big difference. If you're going to be doing double star work, a lot of high magnification, you're probably not going to want to do it very low. Well, why is that? Well, that has to do with air mass. Stuff like that. So you can think about all the things that might affect where you're going and how you're going to do it, and what you will be most successful in doing so. And so along with that, then I am going to spend a fair amount of time on the different AL projects. What are the novice ones? What are the intermediate? What are the advanced? What are the ones that are best suited to urban skies? What are the ones that are best suited to dark skies? What's the sequence of events if you want to go after your master observer project? All that kind of stuff. And I've been told that it's 2 hours. It's a really long time. So there's a lot. Hopefully there'll be time for questions, and hopefully I'll be able to make the presentation enjoyable enough that you won't leave after the first 10 minutes. So there you have it. That's kind of what's going to be going on. I hope it'll be profitable and enjoyable for people.
Thank you, Jerry. It's Rush. If you're on, if you have something you want to add, certainly chime in. So there it is, January 22nd at 1 p.m. That's a couple of weeks, I guess. It will be recorded and posted up there on the YouTube, on the MAS YouTube. So that's that. All right, moving along. Father Brown, I know, is always looking for Gemini articles, and if you read the Gemini, you see the breadth of the scope of the possibilities of all the possibilities of articles that you could write. And I sit here and I talk about that, and a little bit of a hypocrite because I should sit down and write an article myself. But I don't know, where do I find the time? I can use the excuse that I'm working on the budget now, so that works. So so if you have an article, you have something, a story to tell, write it down, submit it to Father Brown. If he wants more, he'll certainly get a hold of you. If it needs big edits, I'm sure he'll help you with that also. And he and his team, him and Brian, I certainly think that they can help you. They'll help you get where you need to be to publish your article in the Gemini for all the membership to read. So thank you. If you have something, please submit it. So better know constellation, not this month, because I want to introduce Bob and Caitlin, who are with a local regional chapter of the IDA. They have a brief presentation that I thought would be very interesting to this audience and our club. I think this is a very interesting project that they're working on. I know I'm interested. So take it away, Bob and Caitlin.
Okay. Well, hi there. I'm Bob Foucault. I've been a MASS member for quite a few years, and recently I became part of a group that's organizing the new regional chapter of the International Dark Sky Association, and it's called Starry Skies North. I'm sure most of you are aware of IDA, but there hasn't been an active chapter in the Twin Cities region, as far as I know, in the past. There's been a chapter in Duluth that started about 10 years ago called Starry Skies Lake Superior. And that chapter is now part of Starry Skies North also. So you could go to the next slide, Mark, I think. So our members are really concerned about a wide range of effects of light pollution, from limiting our viewing and interactions with the night sky, but also to effects on birds, insects, wildlife, health, and safety. And although the challenges are daunting, the Duluth chapters have actually had some good successes up there. They've influenced the street lighting changes in Duluth, lowering the Kelvin temperatures quite a bit, changing the design. They're working with Essentia Health Complex, the big health complex that's going into Duluth right now. They're working on exterior and interior lighting policies and exterior lighting design. They helped get IDA designation of Dark Sky Park and Dark Sky Sanctuary for Voyageurs National Park, Quetico, and Boundary Waters. There's been quite a bit of news about that over the past 6-8 months that happened. In Minneapolis, we're just starting out, but we've had a presence at some community events such as the Monarch Festival last September. We're working with Wood Lake Nature Center on being designated as in Wood Lake and Richfield, being designated as an urban night sky place, increasing their emphasis on awareness about night sky, focusing on dark sky preservation. So we're establishing goals and strategies that involve advocacy, awareness, education, and action. And we're looking for people to join us and work with us on this. And one project that we're just embarking on is establishing a network of sky quality meters to measure the quality of the night sky at a variety of locations in the Minnesota and Wisconsin regions, whatever we can get participation in. And we're looking for partners, and we're also trying to find out, are there any sky quality meters in use out there right now? We've learned of a couple of them in Duluth and some other areas. And so that's part of what we're looking to find out. And Caitlin can talk more about what the project involves and kind of how it got started.
Yeah, thank you, Bob. And thank you all for having us on. I know Bob is a member, but I am not, although I am an astronomer or astrophysicist by training. So I've had my fair share of observing nights in southern Arizona under beautiful, pristine dark skies. It's just amazing. But actually I grew up here, so I'm thrilled to be back in Minnesota and doing some advocacy work through Starry Skies North. If you want to go to the next slide, please. Thank you. Okay, so just in the past couple of weeks, we sort of fleshed out this vision for what potentially a sky quality meter network across the region might look like. And so basically, it's a lot of text here, but I know you guys can go back and read it later. But what we're doing is establishing a network of permanent, so installed in weatherproof housing, sky quality meters across basically whoever will have us across Minnesota, potentially up into Canada, Wisconsin, the Dakotas, etc. We're really hoping to provide publicly accessible data and some interpretation of that data. Really big focus on the public accessibility here, which I know many of you might be interested in as well, getting your hands on, doing some of the fun technical analyses of it. Ultimately, there's lots of different uses of data for the network. I could go into a lot of the details. I'm a scientist by training again, so I can get very, very detailed with it, but a couple bullet points there. One of the big ones is to inform public policy and lighting ordinances, to tell us where we can do better in terms of lighting ordinances, but also to measure what impact they do have once they go into effect, to hopefully get that snowball rolling and ensuring other places across the region do better in terms of their lighting ordinances. So what we are doing is we're proposing a pilot at Wood Lake Nature Center in Richfield, Minnesota, where it's just a couple miles from MSP, the airport. So obviously lots of light pollution here, but as Bob mentioned, we're trying to get that certified as an urban night sky place. So this is a perfect sync up of installing this meter with the aims of the dark sky, excuse me, the night sky designation. Next page, please. So this is just a quick overview of some of the meters that are commercially available. They'll cost you a couple $100. You can also get them on Amazon. There's a couple different versions depending on if you want a wide or narrow field of view, if you want a data logger one, or you want to connect to Ethernet to automatically record the data. It does require a Wi-Fi connection. And you can see there on the very far right, there's some weatherproofing that they provide as well, which is great if you're installing this, in Minnesota where we have very real weather. Next slide. Yeah, so this is the one that we think we're going to be suggesting that people use in the network. It's a data logging light meter. And you can also just go out to Unihedron and browse their website. They have a lot of technical information. It's great. And a lot of suggested uses, some that we didn't even think of as well. Next slide. So this is not a brand new idea. This has been in place in Oregon for just a couple of years now, and we've synced up with them. They have an IDA chapter in Oregon that we're hoping to learn a lot from. So they run a network of many meters across the state. It's just a quick snapshot slide of some presentation materials they've shown. So they have the Unihedron meter and that weatherproof housing you can see, and with the map there, you can see where the meters are scattered across the state. So pretty big region, which is excellent to see. And they don't have the ones that automatically download, but that's because they're sort of out in the middle of nowhere and they don't have Wi-Fi. And so what they do is they actually send out a team of volunteers to download the data and upload it to their database. They also produce publicly available reports on finding some interpretation from the data, which anybody can access. It's on their site. It's really great, very thorough reports, which is awesome with some really technical details. So we're in touch with them to learn from their approach, hopefully learn some lessons that they've learned the hard way so we don't have to learn. And ultimately, I'm really interested in how their data are being used. successes they've had, some case studies as well. So next slide, please. Yeah, so thank you. As Bob said in the beginning, the reason we're coming to you guys here is that we're hoping to learn about any sky quality meters that any of you might currently have, and whether MAS would consider adding them to the observing sites across the state. So this is a really nascent project, but we're really excited about it and hoping that it can become a partnership across several different regional organizations. So happy to take questions if anyone has them now. Otherwise, both of our emails are right there. Happy to respond to email or set up sessions later as well. Turn over to Bob if you have any final words.
No, I'm looking at the chat right now, and Jerry's asking about is there involvement opportunities for MAS members who take SQM readings currently from suburban metro locations, and then Christopher also asked said several of us have the SQM L handheld version, and yes, that's exactly what we're trying to find out. You know, who has them. I mean, we're looking at setting up some data logging ones that will capture the data continuously, so that we can then build that kind of database. But we're also looking for any handheld meters we can, so then we can input that data also as it's acquired, whenever it's acquired, and in a variety of regions. So we're going from the heart of the city here in Richfield to northern Minnesota, and so we want to especially the suburban locations, I think, and the locations where like ELO and Cherry Grove, to measure, how is the sky changing over a period of time, and how can we mitigate that? So the answer is yes, and we don't have the exact plan in place yet, but we definitely want to network with people and collect that data. And the SQM-L, that's the narrow field, with the narrow field lens, and that's the preferred way of taking the readings. I think the earlier version was a wider angle, and so you don't get as accurate of a reading. You're trying to take a smaller field of view, directly from the zenith point, and so we're definitely interested in any SQM-L versions that are out there, handhelds.
All right. And we do have a question from Steve Schmidt. Can you explain further what you would like to do with the SQ data as you accumulate it? I think maybe a little more detail on that.
Yeah, sure. So right now, it's all just ideas and brainstorms. Ultimately, like I said, we're hoping to have it publicly available as something that you can download the files and you can do it with it yourselves, something that would support whatever goals you have. Personally, what I'm really excited about is to be able to go to policymakers, to city planners, and be able to say, hey, this city has sky glow of whatever X. Here it's Y. Theirs is less than us. Let's go to them and look and see what are their lighting ordinances, what have they done to control that sky glow, and what can we implement here. And long-term, again, addressing those long-term trends, over weeks, months, years. Bob, were you going to jump in and say something?
Oh, go ahead. Keep going. I'm sorry.
Yeah, sure. No. Also identify hotspots potentially of sky glow to reduce those quickly. If a big Costco goes up, or a big gas station, something that has very bright lights, we'll be able to identify that and have actual evidence to go to policymakers and city planners and say, hey, please do something about this. There's also some really interesting work that's been done in terms of social justice and equity, correlating sky glow across metro areas with demographics, and actually having data and evidence to show that people of color are more impacted by sky glow because they live under brighter skies. Things like that. So there's a wealth of different uses for these data. I also would love to have a website where you can log in or not even have to log in, to publicly available, and see, okay, what's the sky conditions for the past month or whatever in observatory X, and be able to know exactly what you're dealing with.
Okay, thank you. Go ahead.
We have we're trying to schedule another meeting with the Oregon folks, and to go more in depth on what are they using, how are they using the data, and how are they using it publicly and in an advocacy kind of manner.
I have a practical question. So you have the weatherproof housing on this thing. Let's say it's out at a remote site and you happen to have internet connectivity, so you don't really have to go out there. How do you get the snow off of the top?
Yeah, that's a good question. It's not like they're heated or anything. So, I mean, honestly, I don't know. We haven't thought that through. Good question.
Well, there are sky cameras and things, you know, and such, and I just don't know what is out there for that, but it's an interesting question.
Well, this, you know, and you know, we can't emphasize more that it's a new project that we're starting up. And I had approached Mark, you know, just asking, does he know, or how can we find out, you know, if there are people, you know, meters out there and people that might be interested in collaborating on this. And he suggested that we do a little presentation here, and it was a good opportunity just to introduce the new IDA chapters that are starting up here too. So.
Yeah, it reminds me of the Coco Raz and other people who do observing for precipitation and snowfall and stuff like that. You know, what you're kind of public sourcing the information, and that's a great way to go.
Mm-hmm.
Yeah, I've got one in my backyard for Weather Underground. Same thing or similar thing.
Okay. Thank you very much, Caitlin, Bob. You know, like I told you before the meeting, is I'm considering, I'll probably put one in my backyard and it'll be automatic. So that's and I do participate also in the Weather Underground thing. I have my weather meter, my weather station is logging there too, so that's kind of cool. So I get that. I understand that. I understand how that works. So so thank you very much.
Okay.
You know, in membership, you know, however you want to be involved, here's another opportunity. You know, take it for what it's worth. Get involved if you want.
Yep, we'll report back, and you know, keep everybody in the loop here, and our emails are there. So welcome to hear from you. So thank you very much.
You bet. Thank you, Bob. Thank you, Caitlin. I talked to Jerry. I know there's no awards this month. He's not planning to do anything, but he wants to remind you to get out there and observe. And you know, I know it's going to be difficult this weekend, or at least tonight anyway. So that's all we got. So next month, we do not have a featured speaker yet. I've been in contact with Ahmed. He's working hard. He's looking for somebody, but for some reason it must be difficult for the month of February. People must be busy, or he's just having a hard time getting a hold of people because, you know, they're just getting back in the grind after the holidays. So I'm confident that he'll bring us something for next month. So in the meantime, Professor Skillman is, I know he's on. I saw him on the chat list, and I look forward to his presentation. Welcome to our meeting. You know, as always, we enjoy having you and the rest of your colleagues from Minnesota Institute of Astrophysics. So take it away.
Okay, let me see.
There you go.
All right, and now, how's that looking?
Let's take it away.
Move this down here. Okay, thanks so much for the invitation. I always enjoy speaking to this group. I think my last time was when you had your national meeting, and I talked about the Andromeda project. Before that, I think was at a star party up north. I really enjoy the group, and I'm, you know, always try to say yes when I get invited. This talk is going to be new for me. This is I've worked on this field for since before coming to Minnesota, which was in 1989. And I've never given a public talk on this. They've always been technical talks at conferences and things like that. But I thought it's time I should try to share this. And I think that the Minnesota Astronomical Society membership is probably a bridge between a public talk and an informed talk. So I'm going to try and see if I can do this. The reason being that my contributions to this field, I think, are quite technical in nature. And I worry that I'll be attracted to just get down into the weeds, because that's where I've made my contributions. And so I'm going to try and stay out of the weeds and give you hopefully enough background to actually understand my contributions in this field over the last few decades, actually. It doesn't want to go forward. Just a second.
Yeah, our group likes the weeds.
There we go. All right. Well, so I'm going to start out. I'm going to give context here, and the talk is a combination of understanding, the Big Bang nucleosynthesis is the essence of things. Primarily, helium abundance comes out of Big Bang nucleosynthesis. It's all related to the Big Bang. So I'm going to review at the sort of introductory astronomy level our model of the Big Bang. But I'll take a deep dive into various pieces of this things. And if there's a slide in here that you just are not following, don't worry, I'll come back up for breath in a subsequent slide. So, all right. Let me step through that. Okay, so the Big Bang model is our current model for the origin of the universe. In this model, early on, there's this period of nucleosynthesis where the hot Big Bang gave rise to the production of some light elements. During that, there was the process resulted in an excess of helium, which we refer to today as primordial helium, which we observe everywhere in the universe today. And that measuring that number, how much helium was created in Big Bang nucleosynthesis, actually provides a constraint on our models of the evolution of the universe. That has changed with time, and I'll try and share just how that has changed. This is our model of the Big Bang, which is, I think, quite remarkable. They have a straight line and a log-log plot represent our model for the creation and evolution of the universe is to me, it's just a remarkable thing. But it's just, I'm putting this plot up to remind everyone that, it started out very hot and dense. As it expanded, it cooled. And the model starts at incredibly small time increments there, fractions of a second. And then it comes up to present day where you've got, 10 to the large number of seconds. But that first from 1 second to 5 minutes within that model, that's the period of nucleosynthesis that we're going to be talking about. So the model, the Big Bang model, has really three legs of the observational support. And the first was, of course, the observation of the expansion of the universe, which dates back to the 1920s. It's a little bit controversial these days exactly who did what, but various people all found the same answer, that the universe was expanding. That simple idea that the universe was expanding led theorists to think back to what that meant at early times. And so they thought, well, there must have been a very warm period where nucleosynthesis could take place. And so they went through these ideas about, how the universe itself could be the same temperature as the center of our sun and convert hydrogen into helium and even heavier elements from that. And that was proposed in the 1940s. And then approximately at the same time, there was this realization that as the universe grew at a later time, some hundreds of thousands of years into the Big Bang, that matter and radiation, which were so closely coupled, would decouple at that point, and that we would be able to observe that radiation left over from that. So these are the three primary pillars of the Big Bang model, and I'll dive into the two of them. I'll talk a bit about Big Bang nucleosynthesis, and then I'll talk a bit about the microwave background, and then we'll see how the two are combined to be very powerful tools for studying our universe today. And so Big Bang nucleosynthesis, since the universe starts hot, cools, it can make light elements in that transition where it goes from very hot so hot that particles don't survive to cool enough that particles will survive. And so a little bit of theory, a little bit of knowledge of physics allows you to predict exactly what comes out of there. So this slide here is a reminder of what's happening in the early universe, is that you have photons, which are just pure energy. They can come together and create matter. They created in matter and antimatter pairs. But the matter and antimatter and the photon they're coupled to each other. There's the same, the temperature, which is the average energy per particle, is the same for the radiation as it is for the particles. And so just this matter changing to energy and back and forth, following, of course, Einstein's equals mc squared. The very early universe was this plasma of things just, trading back and forth between photons and energy. But things cool down due to the expansion. And at a certain point here, I've got it at a time of 10 to the minus 5 seconds in the model. You convert from when the matter that you're seeing are the, things like individual quarks, and then you get to a low enough temperature that the quarks can stick together and form hadrons, protons and neutrons. And so this transition happens at a temperature that's hotter than the center of our sun, but not greatly so. And so you'll see here, this I've got, a temperature for it. Also, I've got an energy because, the temperature is average energy per particle. So it's just two ways of looking at it. And then, so this annihilation of matter and antimatter left a small amount of matter. So things were, and this is not understood to date. Our universe, it could have been just totally radiation. If the ratio of antimatter to matter had been perfectly one, all the matter and antimatter would have come together, would have just created photons, and we'd be living in a universe of just light. But there was a small asymmetry there. And what we call matter today was left over from this. But it's a very small number. For every 10 to the 10th photons, there's one baryon, there's one proton that comes out of this. And I'll use that little Greek eta there to indicate the baryon to photon ratio. But so coming out of the early universe, it's a radiation dominated universe. There's a little bit of matter in there, but mostly it's just light. Now, the trick to understanding primordial nucleosynthesis is to follow the neutrons. You're not going to follow the money unless you're going to follow the neutrons. And so we've got when these annihilations stop happening, you've got a lot of protons and a lot of neutrons now are left over, and the average photon's not strong enough to destruct or create. And the ratio, because the protons and neutrons are about the same mass, the ratio is about 1 to 1. But as the temperature falls further, the neutron is a little bit more massive than the proton. And so you start creating protons preferentially to neutrons. And so you get a little bit of an excess of protons relative to neutrons. And this continues on till you get, we're now at a temperature below 0.8 MeV. If I go back just one, you see we started this transition at 1 GeV. So we're down by a factor of 1,000 now. And the ratio of neutrons to protons freezes out where the neutrons are now a minority. There's one of them for every 6. And I'll show a graph of this in just a minute. The neutrons, of course, are not stable. A free neutron will decay. It decays into a proton. So once you don't have enough energy to create neutrons and protons out of radiation, your number is at first fixed. The protons are stable, the neutrons decay, and so neutrons continue to decrease and turn into protons. So that number continues. I'll show this graph in just a bit. And so today, those neutrons, cutting to the chase, those neutrons are found in helium nuclei. All of the free neutrons that didn't find a residence in the nucleus of an atom are going to decay. And that decay time scale is about, the half-life is about 10 minutes, or the average life is about 14 minutes. So very early on in the history of the universe, all those free neutrons decayed into protons. So let me go to this next graph here, which shows you just, the temperature is decreasing across the x-axis here. You can see so the temperature is decreasing. So time is going this way. The neutron to proton ratio starts at 1 It starts decreasing, as we said. It comes to a point where there's not enough energy anymore to keep it in equilibrium. And so then it just continues. It's sort of frozen out at that point. But here is the actual number of neutrons that survive. If none of them got into nuclei, they'd all decay and would be all protons, but they get captured into nuclei, primarily into helium nuclei. And so this is this primordial helium nucleosynthesis. Now, the calculations, the theoretical calculations that make these predictions have a network of, and this is just the most important processes shown in this network. But you run this network, the early codes to do this were written in the 1960s, actually, but have been refined with time. So you have all these different nuclear reactions that are going on. They're all temperature and density dependent. And most of these have measured cross sections today. So, and those cross sections are input into the network so that you can find out how this network will produce things. And so you start down here in the lower left-hand corner with neutrons and protons, hydrogen nuclei, and those are what seed through nucleosynthesis. This is the deuterium nucleus. This is 3 helium, an isotope of helium. This is stable helium-4. You can go from deuterium to tritium to helium. Rarely, if you have enough energy, you can create lithium and beryllium in this process. But the majority of things are happening right here where the neutrons and protons create an amount of helium in there. All right, this is a bit of a, we call it a spaghetti plot. It's a bit of a complicated plot, but in fact, it's not that complicated if we just concentrate on what we're interested in. This is the result of all doing that network of calculations and looking at it as a function of temperature. So here, early in time, it's a high temperature. Notice the units 10 to the 9 Kelvin. High temperature going down to low temperature. So this is going forward in time. The black line at the top is the protons, and they're stable, so they're really not changing, and they've already come out of this freeze out. The red is the neutrons, and you see the neutrons are decreasing, and that's because some of those neutrons are decaying into protons. And then here, within these first 5 minutes, a lot of things happen. This line here is the production of helium, where the neutrons are finding their way into helium nuclei. The hydrogen, you can see the protons decreases just a bit because there's protons that go into the nuclei too. And so this is the helium, this is the protons, so the hydrogen, and so that ratio is fixed in coming out of the Big Bang. These other light nuclei are produced, and lithium and beryllium and boron not so much actually, but deuterium are produced here. And notice again that this is a log plot. So these are well down. These are, many orders of magnitude down in abundances. What really comes out of Big Bang nucleosynthesis is hydrogen and helium. Okay. Now, this is a so-called Schramm plot. It's named after David Schramm, who was a professor at the University of Chicago, who made some very important contributions to this. And it's the predictions from the theory. I'll grab my cursor again. Here we go. This on the left side is the prediction from the theory of the production of the various light elements. Y is shorthand for helium, deuterium, the isotope of helium, 3 helium, and lithium, as a function of the baryon to photon ratio. So our universe has 1 baryon to photon ratio, but we can calculate through theory what the ratio of the light elements would be as a function of that. And the interesting thing here is that you see helium changes over an order of magnitude in the early density. It changes only about a factor of 10%. Deuterium changes about 2 orders of magnitude over that same change, 1 order in density. And lithium does this interesting thing, which is due to the fact that there's processes that both create and destroy lithium. And so those two are in competition with each other. But these are the predictions of Big Bang nucleosynthesis. You just start with the idea that the universe went through this phase where it was extremely hot and then cooled. And then you can pick an individual, what you think the baryon to photon ratio is, and you get a set of predictions. And these over here are just the uncertainties on these. Those uncertainties are tied to the physics of the various processes, the cross sections for the nuclear processes. And you see that the helium calculation is really very well known. All right, so we're going back now 3 decades in time, And the game was, if you could measure helium and deuterium and lithium, measure the primordial values of that you could place them, that's these three rectangles here, place the observations on this theoretical prediction curve. If there were concordance between the three, it would predict what the value of the density of the universe was, or the number of protons and neutrons relative to the number of photons. So that baryon to photon ratio could be calculated by making these measurements. And this is about the time, I was a few years before this actually, when I started getting involved in, and I was working on making observations of helium and inferring the primordial helium abundance. And that's 30 years ago. Things have changed a bit, and that's this next part is that the microwave background observations came along. So at about close to 400,000 years after the Big Bang, the universe cooled to the point where hydrogen recombined and could no longer be ionized. Okay, so we're not talking about nuclear processes here. We're just talking about the average photon could ionize a hydrogen atom, remove the electron from hydrogen at that point, and then it would recombine. But as it gets cool, the average photon's not energetic enough to ionize hydrogen, and that's when radiation and matter decouple. I have a little diagram here to show visually what's happening here. So when things are hot, and the temperature at the time is now in the thousands of degrees, right? Not millions of degrees, but at thousands of degrees. At this point, you see the nuclei, that's a helium nucleus, that's a proton, all little gray things are electrons. The electrons are free because the average photon could ionize the electrons away from the nuclei. As things cool, the radiation became lower energy. Those electrons recombined, and you see now they're grabbed on, those little blue dots are grabbed on by either the hydrogen or by the helium. And so now, because all the electrons are bound to nuclei, the radiation is no longer interacting, being scattered by, you see the photons are these wiggly yellow lines. And so the electrons are not, the photons are now free and free streaming through the universe right to our observatories today. So this radiation, which was released when the universe went below 3000 degrees Kelvin, is what is observed as the microwave background today, which I think this is probably, review for most of you here. And this was, first detected by Penzias and Wilson at AT&T Labs in 1965, which they later received a Nobel Prize for. Now, today, you fast forward another 20 years, well, 30 years after, and 40 years actually after the discovery, and that uniform radiation, which is a single temperature, which is seen throughout the universe, has variations of it on the order of 10 to the minus 5. These variations in that radiation field, variations in temperature of the radiation field are very, very small, but they've grown from the original variations in the radiation field, which were tied to the quantum mechanics of the small particles that gave root to the structures in our universe. So observing these small variations, and this is an image from the Planck satellite, gives us a powerful diagnostic of the cosmological parameters. And this is not at all, in my dealing with teaching students, this is one of the hardest things to communicate. So I'm going to spend a little bit of time on this. I imagine you've had Clem Pryke talk about this before and others, but I'll just try my shot at how it is that these variations in the microwave background can give us a powerful diagnostic of the cosmological parameters. Now, this graph, this is how you see that image represented. And you see on the x-axis here are angular separation on the sky. And what you're looking for are correlations on various angular separations. And you see at about 1 degree separations, there's a lot of power, meaning things are highly correlated. The structures in that image seem to have mostly be dominated by this one angular separation, so on the order of 1 degree. And so this plot here, which is now iconic within astrophysics, this represents our universe. Where do the cosmological parameters come from? I'll focus on just a single one, All right, this is that same graph, only what we've done, and this bar is raising and lowering the matter density in the universe. If you will, this is the same number as the baryon to photon ratio. And so when that number is high, you see that the so-called odd peaks, 1, 3, and 5 are high. And when it's low, the odd peaks are almost the same as the even peaks. So the observation of the pattern of the background radiation on the sky imprints in it the diagnostic of various cosmological parameters. This is just one of them. That's the baryon to photon ratio. It also imprints, for example, the expansion velocity of the universe. The place of this first peak is done that, and various ratios of peaks are given like that. So just the theoretical interpretation of these curves ties directly to a unique universe with a unique set of cosmological parameters. And it's only with these when this graph was really highly detailed that one had a strong constraint on that. How does it, what's the physics behind the effect of matter on those things? Well, if we go back to think in terms of musical instruments where they have a fundamental and a first overtone and second overtone, that sort of thing, we can imagine for a minute that the universe, early universe, has structures like that. It has a specific size at which things are, that sort of, just like the flute had a specific length. In the early universe, there were scales that were preferred. And here on the left, it's showing just matter distributed randomly. But gravity clumps things up, and clumps things up where things are densest. So you have preferred scales here, which are enhanced by the presence of matter. The stronger the matter is there, the more that this is enhanced. If you think now in terms of the second overtone, which would have a peak here and a valley there, that would be destroyed by the presence of this. So the clumping of matter affects the spectrum of those variations in the microwave background. So it's very sensitive to the various cosmological parameters. And here's just we go back to this spectrum here, and we see that at large scales, there's not a lot of structure, and at fine scales, there's not a lot of structure. But here at this 1 degree scale, you see a lot of structure, and that's this peak in that spectrum. So if you buy that, this is, by the way, I'm sorry, I should have replaced this. This is the W map. Probably you can recognize it, not the Planck map. So that's the first map that came through that allowed this, and then Planck came through with a more precise measurement of this curve. But the amazing thing is that because of the fine structure in here, things are encoded and measured very precisely. That's one of the cosmological parameters is age, and the age is 13.8 billion years old, or as they say in the build up to the Big Bang Theory, nearly 14 billion years ago. It's interesting to me that age of the universe, we know that better than the age of the Earth. And it's just because of all the power in this spectrum that we get that. Now, for the purposes of Big Bang nucleosynthesis, the cosmic microwave background allows us to measure very precisely the density of baryons. That's why I picked that out as an example. And so we come forward, because of modern microwave background radiation measurements, we get a very accurate measurement of the baryon to photon ratio. So in the last century, the concordance of the primary light element abundance was taken as support for the Big Bang theory, and additionally as a method to measure the baryon to photon ratio. Now, in present day, the high angular resolution observations of the minuscule variations of the cosmic microwave background radiation have surpassed the accuracy of the light elements in measuring the baryon to photon ratio. And here it is. Here's that Schramm plot. So these are theoretical predictions here. And that narrow little yellow line there, that's the baryon to photon ratio as measured by the microwave background. So now we've gone from trying to measure the light elements to deduce this to knowing this from the microwave background. And now the idea is, do our measurements of the primordial helium abundance, the deuterium abundance, and the lithium abundance, do they agree with this prediction of the combination of the microwave background measurements and Big Bang nucleosynthesis theory. And you see here, this YP, that's the primordial helium abundance, that's known to approximately 0.1%. That's the prediction, the accuracy of the prediction from our microwave background combined with the theory. Now, I've been in the business of measuring helium abundances in various systems and trying to measure helium abundance in nearby systems and infer what the primordial helium abundance meant. So I'm not going to step you through what it is actually that I do. All right. So first of all, this is the kind of, oh, sorry, didn't mean that. This is the kind of plot that I'm trying to work on. If I can measure helium in a whole lot of objects, and then if I measure a slight slope there, because I'm plotting it versus oxygen abundance. So each of these points is an individual galaxy. I measure the oxygen abundance there. I measure the helium abundance. I put it on a line here. I'll show you an expanded plot in just a second. And then extrapolate that line back to 0 oxygen abundance. That would be what happened before there was any stellar nucleosynthesis at all. And that would be my prediction of the primordial helium abundance. First of all, you notice that everywhere I look in the universe, there's a large abundance of helium. And it's about the same everywhere. And that's your signature. That's the primordial helium. Over time, stellar nucleosynthesis will create helium, release it to the interstellar medium, and enrich things. But from this diagram, you see that oxygen is enriching much faster than helium is. But this is the game. Get accurate measurements here, extrapolate back to there, and that's the idea of what we think the primordial helium abundance should be. How is that done? Well, in star-forming regions, the most massive stars produce a lot of ultraviolet radiation. That ultraviolet radiation turns the surrounding gas into a plasma. That plasma emits an emission line spectrum. If we can, and I'll show an example of that in just a bit. If we can interpret that emission line spectrum, we can infer relative abundances of different elements. And so to do that, we have to first measure the temperature if we can, measure the density if we can, and calculate the emissivities. Emissivities are the numbers that come from the theorists that tell us for a certain amount of material at a certain temperature and a certain density, you would expect the emission line to be this strong. And they change, all these things change. So we have to do this, you have to make these measurements quite accurately. Now, we look at different lines from different elements, and then we can get relative abundances. And then finally, the last step is if we measure helium and we measure oxygen, both relative to hydrogen, extrapolate to over H, and that's where we get our primordial helium abundance. Here's an emission line spectrum covering just the blue part of the spectrum. There are familiar lines of hydrogen here. Don't click on it too much. Hydrogen, H beta, H gamma, H delta. There's the nice hydrogen sequence that goes through there. There's some oxygen lines. These are so-called forbidden lines of oxygen. And there's some helium lines. So if I can measure the temperature, and I can do that one way is by measuring the ratio of these two oxygen lines. There's that little faint line relative to one of these two strong lines gives you a measurement of the temperature, because one is an upper level and one is a lower level, and the upper level is very temperature sensitive. So you can measure here the temperature sensitivity, the temperature of this thing. You can convert those oxygen abundance lines. You've got an oxygen double plus line here and an oxygen single plus here. So you measure those two ions, combine them, you get a total oxygen abundance. There's your oxygen abundance. You measure these helium lines relative to the hydrogen lines, you get a helium abundance, and then you're off and run off to the races. Now this was done, this plot comes from 2004. And in 2004, here's the result. Doing that, you can see here's a number of different galaxies measured. You can see the slope now in this expanded plot. The extrapolation back to 0 is not really a very large extrapolation because we focus on getting as low a metallicity as possible. And you extrapolate that back and you have a prediction of what the primordial helium abundance should be. And it's got a 1% precision. And this is now 18 years ago. So at this level, 1% seems pretty good. And you think things are pretty much done. And here's where, this is the part where it's science. Okay. Keith Olive, who's a professor at the University of Minnesota, who's a high energy theorist, and myself have been working together. And in 2004, the same year that that plot came out by our colleagues, after studying how we derived helium abundances from those spectra, we came to this conclusion. The observational determination of the primordial helium abundance is completely limited by systematic errors, and that these systematic errors have not been fully accounted for in any published observational determination of the primordial helium abundance. Now I'm looking at these 18 years later, and I'm thinking, whoa, you know, I probably could have been a little more diplomatic about that sentence, but there it was. We put several years into trying to understand some very subtle effects, and had basically come to the conclusion that several of the uncertainties that needed to be calculated were underestimated in most of the literature at the time. Now, this is a little history plot here. These are measurements of the primordial helium abundance from the very first one in the 1970s up through when, 2004 is when we published that paper here. This is the first measurement by Manuel Peinbert, and he measured the helium abundance in the Milky Way and the helium abundance in the Large Magellanic Cloud, took those 2 points, extrapolated that back to zero, and got this measurement, which was, this is the origin of the whole field. So this is a very famous paper. Peinbert's a very famous nebular astrophysicist. And this point came out a few years later. He added the Small Magellanic Cloud, and you see it improved the accuracy a bit. This dashed line across the top when this plot was made was the inference from Big Bang nucleosynthesis theory and the microwave background fluctuations. It doesn't come out until, you'll see in a later plot, it comes later. It was simplest just to kind of guide where things are going. And you see there's kind of what I would call a checkered history here. And this is Keith Olive and I, this is our first attempt to join the field. We made some new observations. We published them. We followed standard procedures that had been set by these previous things. Because we found some very low oxygen abundance things, that extrapolation was very small, we very confidently entered the field with this. And then we worked, you see, this is, you know, mid 1990s, and it's almost a decade. We worked on better understanding all these subtle effects. That's the weeds I promise not to get into. There's all sorts of corrections that go into things that I promise not to show you the energy level diagram of the helium atom, but it's quite complex. And in the end, we said, honestly, we think, taking all the measurements in the literature at the time, we think that this is the best uncertainty, the most honest uncertainty that you can have at the time. Normally, in your career, you don't want to spend 10 years to increase the uncertainty on your measurement. But we felt that this was a valid contribution. We felt that the previous work before had not taken into consideration all of those uncertainties. And you're measuring a fundamental constant. You can't skip things. Now, you could say that Keith and I were very slow. It took us a decade to get there, and I think that would be quite appropriate criticism, but we weren't working with any students. And Keith had been saying for several years, we have to have a student. And so Eric Aver was a graduate student at the University of Minnesota in physics, and he started working with Keith and I, and things took off as soon as Eric got involved. He took he took to heart what we had said, we have to do a better job on this. And we explored, first of all, there were new atomic calculations. So there were new emissivities, everything had to be redone anyway. I had this idea, the old procedure would be stepwise. You take the hydrogen lines and you calculate the reddening, and then you take the oxygen lines and you calculate the temperatures, and then you take the helium lines and calculate the helium abundances. And it seemed to me that all needed to be done in a single process if you were to better understand the uncertainties, and that's part of the work that Keith and I did. And then I showed you an emission line spectrum. There's some stars in there. Stars have absorption lines, so there's absorption underlying that spectrum. The hydrogen, this is a real subtlety, but you either have collisionally excited lines or recombination lines. Hydrogen is predominantly, it was thought to be entirely recombination, but there's a collisional component, so we had to add that into that's one of the subtleties that had been missing in the error things. And so Eric got to work and did that. And it turns out, and now we moved to this new paradigm. We were going to determine everything from just the hydrogen and the helium lines. There's the emissivities have temperature sensitivities so that we can derive the temperature and density just from the hydrogen and helium lines. And we came to this conclusion that what was really stopping us were certain degeneracies. Here's an example. This is the main degeneracy. So for a given solution, so you have a set of hydrogen lines and a set of helium lines, and you're trying to solve everything simultaneously, you get solutions where it solves for this temperature and it solves for this density. In a standard method, if you want to understand the uncertainty on the electron density, you would hold that fixed and look at the temperature with, at a fixed temperature, you'd look at the range and density. Otherwise, if you held the density constant and you looked at the range and temperature, you'd see at this. But because of the degeneracy between these two, the true uncertainty is this ellipse here. And so you can't go from this simple-minded single uncertainty on each parameter. You have to go to probability distribution functions for each of these things. And it's this ellipse, this banana size, as opposed to these two little crosses here that led to the underestimating of the uncertainties. And there are other degeneracies. So we used Keith and I had started using Monte Carlo already. Monte Carlo analysis is that's what my financial advisor gives me when he tells me, he tells me what year I'm going to die, and then he models the economy over the history randomly, and then tells me how much money I'm going to have when I die. That's a nice use of the Monte Carlo analysis. Markov chain is a sophisticated type of Monte Carlo analysis that pulls out all these degeneracies and gives you probability distribution functions. So Eric researched doing this, changed our Monte Carlo analysis to Markov chain analysis. And then we used the MCMC to derive a new value of YP. And here, this is, reanalyzing all the data that was relevant in the literature. Here's our intercept. That's our prediction of the primordial helium bonds. There's that prediction from WMAP right there. So they're consistent. This is good. We'd like to decrease that. But our result, we felt that the honest accounting for all the uncertainties gave you an uncertainty on that calculation of 3.3%. Now, here's the history jumping forward a bit. There we have that, we think everyone's wrong number. Here's, oh, this is a better number now, and the uncertainties are really comparable. And then this is the Markov chain Monte Carlo, and again, things are comparable. So we're making progress in the methodology. We're not making progress in the uncertainty quite yet. Now, in 2015, our colleagues had pointed out that there's a line in the near infrared. It's not part of a normal spectrum that one takes, but it's a helium line in the near infrared, which has a higher sensitivity to density, a very high sensitivity to density, and that can help break the degeneracy. So we added that line, those observations, into our analysis, and we have a new regression here. It looks similar, but the uncertainty has come in half now, because we're finally getting down to the point with this addition of new information, or getting to the point where we can, clamp down on that uncertainty. The other thing is that you'll notice here, and you may not have noticed before, but the uncertainty on the slope was larger than the slope on the previous things. Here we're actually measuring the slope with a uncertainty that's measurable. And here's a plot. Again, going back to this history, that the dashes here are the red little things are the measurements from the microwave background, and you see that they've changed a little bit in time, but not so much. The blue things are our measurements. This is our new measurement that we were quite proud of, the 1.6% uncertainty. And remember this point here. This is the standard when we came out with this measurement, and it's the difference in how we analyze the data are almost identical in the two studies, but it's on our analysis that things change. And you notice going forward in time, there's two other groups here that have posted numbers, and they've adopted our methodology, and they come up with a similar number to us. All right. So I kind of held back on what it's all about now, because obviously Big Bang nucleosynthesis is not telling us about the baryon to photon ratio anymore, because the microwave background tells us that. It's nice to confirm and be consistent with the predictions of Big Bang nucleosynthesis and cosmic microwave background. But there's something else that studying helium can do for us, and that's that the primordial helium abundance gives us constraints on NF. This is the effective number of neutrino species. And that's a shorthand, but theorists use that for the degrees of freedom in the early universe. So I'll explain in a little bit. All right, so here's that Schramm diagram here. But now the first diagram was assuming the canonical value of 3. We know there's 3 neutrinos. We measured the 3 neutrinos. So the canonical value is 3.0. But you'd like to constrain that observationally. And the Big Bang nucleosynthesis has predictions that the primordial helium abundance changes very sensitively to the number of neutrino species. Now, what's shown in this plot are 2, 3, and 4. We know that there's 3. So the 2 is just to show you the sensitivity. But look at how sensitive helium is to that, whereas deuterium not so much and lithium not so much. So now primordial helium is telling us something very fundamental about physics, the number of neutrino species, or rather the number of degrees of freedom in the early universe. So accurate measurements of the primordial helium abundance give us this nice cosmological constraint. Now, do you care how many neutrino species there are or how many effective neutrino species there are? You've probably been following in the literature this big controversy that the Hubble expansion, if you measure it with variable stars and the local ladder and things like that, you get one set of numbers. And if you measure it from the microwave background, remember the microwave background is very sensitive to all those cosmological parameters. So you get them, and there's this 4.4 sigma difference, and this is quite the controversy today. In this diagram that Adam Rees put together, he said, well, what does that refer to in terms of degrees of freedom in the early universe? Well, there's plus 0.4 almost spreads that. And so there are all these other ideas about new physics to resolve this discrepancy. But there are many. The theorists are always working on new ways of new physics. But one of them is right here on this plot. So that's why we care about NF. This diagram, maybe not so straightforward. I'll see. We'll see how it goes. So here's the predictions of the number of neutrinos you get, the constraints, if you will, given our helium abundance measurements. And then that's these blue, green, and red lines, 1, 2, and 3 sigma lines. And then when you combine them, remember that baryon photon ratio is very well known from microwave background. We're not very constrained with primordial helium at all, but if you constrain where this happens, you get better constraints. And you see that's the numbers around 3. We haven't talked so much about deuterium, but it turns out that the deuterium is so precisely measured these days that comes up with a very similar answer. If you combine them all, you get that number there. Here's the number that's coming out of the Big Bang nucleosynthesis measure, the light element measurements. Here it is when you combine it with a microwave background. So it's close to 3 with a small uncertainty. So it's consistent with 3. But wouldn't it be nice if we could decrease this? That earlier point in 2014, this was the controversial thing. If you took that measurement of the primordial helium abundance, then your number of effective neutrino species is 3.5, which is 0.5 larger than the standard model. And that's why this was a bit controversial. All right, this is just bragging right here. This is the cosmology paper from the Planck collaboration in 2018, and they took our result to make all of their determinations of cosmological implications of things. And I just, that's just bragging, sorry. Anyways, moving on. How can we improve? If you look at this diagram, when I look at this, I say, that doesn't look like a really impressive plot. The number of points is small and the scatter is kind of large. Can't we do better than that? And there's 2 obvious things to do. One is you can add more low metallicity objects. The more you add here, the smaller this extrapolation is. That they have a lot of leverage. And the other is you can reduce the uncertainties on these. And so we thought, we've made progress on both of these. So the first, how do you add new low metallicity objects? The Z is our shorthand for metallicity. Well, we're involved with the Alfalfa project was using the old Arecibo before the disaster happened to do a blind survey in 21 centimeter looking for neutral hydrogen. And we discovered new galaxies we'd never seen because galaxies were dominated by searching in the optical. When we found this nearby galaxy, Leo P. Leo P had a star-forming region in it that made a chemical abundance analysis possible. It's a very low metallicity galaxy. So we made measurements of that and added that to the mix. This is a plot of oxygen abundance here versus the luminosity of a galaxy. This is my former graduate student, Danielle Berg. She's a professor at the University of Texas now. This is part of her thesis work was establishing this relationship. It tells you that the lower the luminosity of a galaxy is, the less nucleosynthesis enrichment is gone in time. And so the lower the oxygen abundance. So if you just go to tiny little galaxies, if you can find bright star-forming regions in tiny little galaxies, you've got the right thing. This is another former student of mine, Christy McQuinn. She's now a professor at Rutgers University. She was involved in the discovery of a second one. She's also involved in the discovery of Leo P, but also involved in the discovery of a second one and placed it on this diagram using Danielle's data again. But she made this, the reason I wanted to do this, she made this very nice plot where this is the graph we were looking before, and you see extrapolate back to here, but there are lots of galaxies here that are low metallicity, but relatively bright. This is, the Small Magellanic Cloud is about here. So they're not really big galaxies, but there's lots there. And then she looked at them as a function of stellar mass, and she found that things kind of closed up a little bit, but there's still galaxies here. Our current understanding is that these galaxies are ones where pristine matter has just fallen on recently, triggered a burst of star formation, and you're seeing a much lower metallicity than that galaxy would have already had. Anyways, what I really want to emphasize right down here in this bottom panel, you see all these recent data. There's a lot of groups that are looking for low metallicity galaxies today, and they're starting to be successful. There was about a 2-decade dearth of progress, but in the last decade, we've seen a lot of progress. And so now we have a lot of targets, new targets at low metallicity to find that. So reducing the uncertainties, this is, we previously used these helium lines here, these hydrogen lines. I talked about you use the fluxes. These are all of those different parameters you have to solve for very carefully. Those are the weeds I don't want to get into. This is the type of equation you use. I don't want to get into that. But the point is, this is the old method. We could improve on the new method. And we did this, first of all, the Large Binocular Telescope, which Minnesota has access to, the modular double spectrograph, provides these beautiful high quality spectra, and you can also look in the near IR with LBT and get that other helium line. In our solution, we'd only been including the optical lines. There are near IR hydrogen lines, which we can include. We can include additional fainter helium lines in the solution. We wrote to people in Belfast and asked for new atomic data for getting a better calculation of the collisional excitation, and they provided that. We've improved that now. And we improved on his sabbatical, this first sabbatical. Eric spent a lot of time working on all these things, but he spent a lot of time working on modeling that underlying stellar absorption. As a result, we took our spectrum from Leo P and we reduced the uncertainty on an individual object by a factor of 2. And so here's Leo P there. With a better uncertainty on Leo P, just that 1 point, the uncertainty went from 1.6 to 1.4%. Doesn't sound so big, I know, but it's like an 85% reduction in the uncertainty. The goal now is to reobserve everything here. Modern observations for all these things, using the LBT, using that near infrared helium line, and we'll be able to, and all of those new low metallicity objects, and we'll be able to fill this up with things with error bars smaller than what you're seeing on Leo P. Leo P turns out to be kind of a faint object. And that's going to happen in the next couple of years because a lot of those spectra already, we have them on disk already. All right, so in sum, Big Bang nucleosynthesis ability to predict the light element abundances with high precision is a great accomplishment of the Big Bang model. Our current determination of primordial helium abundance agrees well with the microwave background prediction Self-consistent analysis of the primordial helium abundance using Monte Carlo Markov chain has proved insightful and effective. More targets and higher quality spectra are needed. And like I said, we have them. We're on the edge of things. And now we get finally to the payoff, right all the way down here. The constraints on the number of effective neutrino species will be significantly tightened, such that that number will come down to less than 1/10 of a neutrino species, which puts us in a regime where we start eliminating all sorts of this new physics models. It becomes a very tough constraint for the theorists to get around. All right, that's the end of my presentation. I guess I'm not sure what's best in terms of.
Well, I saw a couple of questions in the chat. One of them
Okay.
was, will
I
Webb,
can go right to the chat and
yeah,
look at those.
yeah. So start at the bottom. I saw one about Webb. Will Webb help you? James Webb.
Well, I'll start all right. There's don't freeze to death. Budget should be D. Should that D be a B? The D is probably yes, deuterium. Okay. Two heat. Yeah. It's good. Okay. There's a little yeah, spaghetti. Now I'm hungry. Okay. Sorry, I have to leave the meeting. Okay, let's start with, all right, you're right. If I just listened to you, I'd be in the right place. Will Webb help with your work? Not directly. Ground-based optical spectroscopy is really where to go. And Webb's tiny field of view is not a great discovery instrument. And a lot of the lines that we concentrate on are in the optical, and Webb is an infrared optimized telescope, so it's not done there. There will be some indirectly. There will be some things about nebular astrophysics that we will learn from Webb that may help a little bit in terms of our how we analyze our spectra. But I'm on an early science program for Webb, and it has nothing to do with helium abundance. Webb's doing some other things and fantastically well when it starts. But yeah, I really think, fortunately, we have the tools in hand now to do the work that we want. We don't have to wait for Webb on this. Okay, why is constraining NF important when the number of neutrinos is known? Yeah, I probably didn't do a very good job on this. Thanks for okay. So the number of, we know that there's 3 neutrinos. There are theories that are, you have the sterile neutrino, and there's theories where that number is not just 3. But we know for sure that there are 3 neutrinos. Now, N effective is the high energy theorist's way to characterize the degrees of freedom in the early universe. And so it's not so much that we're looking for a fractional number of neutrinos or whatever, but we're looking, is there an extra degree of freedom in the early universe? And it wouldn't necessarily be a neutrino, it might be some other particle. A lot of the ways that high energy theorists solve problems in cosmology is by imagining a new particle with new properties and seeing how it would affect things. And so that's, if it's a new particle, it would be a new degree of freedom in the early universe, and we would put a constraint directly on that. I hope I've answered that better now. How many hours of observing get new measurements, one observation request, or multiple ones to submit? So with the LBT, because the LBT is 2 8-meter mirrors, if we, for most of our targets, 2 hours of observing in the optical and on the order of 1 hour observing in the near infrared, and we have enough to do a target. So going back to do the 14 or 15 points that you saw on the most recent plots, to redo all of those is not an outrageous thing. If we spread it over 3 or 4 years, which is what we're trying to do, we'll be able to do all of the historically important numbers and add about a similar number of very low metallicity objects. So it's not, if it were just coming out of the University of Minnesota, it would take more than 3 years. But my colleague Rick Pogge at Ohio State is dedicating a lot of time on the Ohio State side. So between the two of us, we're in good shape. I'm not sure the number. I know we've got more than 10, maybe less than 15 new observations already ready to go to do the analysis. Yeah, okay. Excellent question. That's why maybe you already know. So can you comment on the apparent low abundance of lithium? Is this an observational effect or some missing physics? Oh, I'm sorry. First of all, yeah, to answer your question, there's the so-called bottleneck. There's no stable nuclei between, so you've got stable nuclei at n equal 1, n equal 2, but you don't have the stable nuclei beyond, if you count the particles in there, helium is 4, lithium is 7, and there's a gap, there's no stable nuclei at 5 and 6. So that's why lithium is so depressed by orders of magnitude, is that very few, remember, when you're hot enough to get up there, you're also hot enough to destroy those things. So things that can work out the network all the way to that and not be destroyed, that's why lithium is so low. I thought you were going to refer to the fact is, to date, one of the biggest problems is that helium abundance looks great, deuterium abundance looks great, lithium abundance doesn't fit on the graph anymore. With that very accurate microwave background number, lithium, there's no agreement between the observational determination of primordial lithium and what's predicted from Big Bang. So this is the so-called lithium problem. And I saw lithium and I just, oh no, I need to talk about that. But the first thing is just that the so-called bottleneck, because there aren't any stable nuclei between helium and lithium. So the chain sort of breaks down there. Is there any link with this research to dark matter and dark energy in the universe? Well, yes, though not my specialty. This is where, we don't know what dark matter is. We also don't know what dark energy is, right? There are many, many dark matter particle candidates, and they all have properties. And some of those properties would affect what happens in the early universe. And our constraint is effectively ruling out. We've had people write, high energy theorists write. Keith Olive is a world's expert in this. So he does not work in alternative particles quite so much. But we have had people that have written us directly and said how important this work is for either letting in or eliminating these various candidates for these things. So yeah, there's a really direct connection between what we're doing and better understanding or better constraining. I don't think we'll ever understand dark matter until we've actually detected the particles. But this helps constrain, what types are still viable candidates. I think that's it for the chat. If people want to...
So are there any other questions within the audience? Go ahead and open your mic and ask away.
I'm trying to figure out how to phrase this question, but when you were showing the cosmic microwave background granularity, you said it kind of maxes out, the dynamics of it maxes out around 1 degree arc in the sky.
Yeah.
And you equated that to like a resonant frequency for an oscillation in a cavity kind of a thing.
Right.
Does that 1 degree equate to something, on the scale of the universe at that age when that was forming and stuff like that? Does that equate to a certain dimension, like a certain size or a certain something else that it's significant, the size of I don't know, I'm trying to think of what would be a good resonant.
That's the size. So early on, way back, you go to the earliest in the Big Bang, and you have the inflationary period where there's not this nice linear growth, there's this exponential growth. And so, and the uncertainty principle determines, so the scale of things that happen there. When the quantum mechanical problems or the quantum mechanical constraints you have there grow through this inflationary period to the size structures that dominate the structure that we then see in our universe. And so there's that characteristic size.
Yeah, I'm not even sure what to ask. I just wondered if
I'm sorry.
It just seems really
no. Your question is brilliant. I mean, you're right. I'm sorry. I don't have the. I'm not a microwave background person, so I don't have the nice textbook sense that I should have. It's my fault. It's not your fault for the question. I'm sorry.
Oh no. Just taking a stab there.
Yeah. But it's just this remarkable thing, right? That
it seems big. It seems like a big granularity. you know.
Yes, and that's the point about inflation, that it grew from these quantum mechanical sized structures into large macroscopic structures.
Thank you.
Any other questions? Well, Professor Skillman, thank you for your time this evening. And, you know, as always, you know, I know I learned something somewhere. I know more about more about helium now than I ever thought possible. You know, so that's kind of cool. So I'm sure everybody else got something out of it. And hey, maybe someday we'll bring you back and you can talk about web. Maybe. What would you think of that?
Oh, I would. Yeah, if the early release science program that I'm on, so it's supposed to execute there's 13 of these programs. It's supposed to be one of the first 13 programs to execute on web. I'm very excited to see that, and we'll be sharing those data everywhere. It's a completely different science theme. It's looking at nearby galaxies, looking at the stellar populations in nearby galaxies to do this sort of archaeology that we do, where we recover the star formation history of the galaxy by looking at the stars that are still there today. And the web, because it's more sensitive and it's in the infrared, will give us a new window on these nearby galaxies. So yeah, very, very excited about that, and be very happy to share those results when they come.
All right, very good. So thank you for your time. Thank you very much. We look forward to seeing you again someday. You know, thank you for your support. Everyone else, hey, we'll see you in about a month. And hopefully some of us you'll see face to face. And like everybody else that it doesn't feel comfortable meeting face to face, the Zoom and the recordings will be there. So good night, everyone. Happy New Year. And take care.
All right, thank you.
Good night.